They told us the math was settled. Spoiler, it wasn't. Number 10. Ancient, massive galaxies. Webb pointed at a tiny patch of sky, a piece smaller than a grain of sand held at arm's length, and there they were. Small red dots. They should not be there. These dots glow with old, red stars. Their light carries chemical fingerprints, carbon, oxygen, elements that only show up after several generations of stars live, burn out, and explode. That chemistry takes time. A lot of time. But the universe in that image was barely a few 100 million years old. It had not had time. Not by any theory we trust. So scientists went through the checklist. Wrong distances? Checked. Lensing making things look brighter than they are? Checked. Instrument errors? Checked. The spectra held up every time. These objects look mature, chemically rich, and massive, and far too early. One explanation is bursty star formation, gas collapsing and lighting up in explosive episodes instead of a slow burn. Another is rapid-fire mergers in crowded regions where everything crashed together and piled up mass in a hurry. Then there are primordial black holes, acting as gravitational seeds that dragged matter together faster than anything else could. None of these sit comfortably. Each one solves part of the problem and opens a new one. What stays with you after all the data is this. The early universe was not a slow starter. Something made it sprint, and right now, nobody can tell you what. Number 9. Early supermassive black holes. Black holes are supposed to grow slowly. They eat gas, radiation pushes back, and there is a speed limit, a natural cap on how fast they can feed. Think of it like drinking through a straw. You can only pull so hard. Webb found a black hole 10 million times the mass of the Sun sitting in a universe that was only 570 million years old. That is not a slow eater caught mid-meal. That is a giant that should not exist yet. The distance checks hold up. The spectra confirm a real, massive object. So the question shifts from is it real to how did it get so big so fast? 3 ideas, and none of them are simple. The first skips the slow growth phase entirely. Huge clouds of gas collapsing straight into black holes without bothering to form stars first. A direct shortcut that gives you a heavy seed on day 1. The second needs a crowded neighborhood. Small black holes slamming together, merging, feeding furiously in regions so dense that the speed limit barely applies. Simulations can produce this, but only by pushing conditions to extremes nobody expected in the early universe. The third reaches all the way back to the first second after the Big Bang. Primordial seeds, born from density fluctuations before stars even existed. Bold, speculative, and very hard to test with current telescopes. All 3 ideas require the early universe to be far more violent and efficient than our models allow. Whichever explanation wins, the textbooks lose a chapter. Number 8. Complex organic molecules. The raw ingredients for life might be everywhere. That is not a philosophical statement. It is what falls out of Webb data when you look at a galaxy 11 billion light-years away. Webb picked up benzene, methane, and a highly reactive molecule called the methyl radical inside an ultra-luminous infrared galaxy. These are not simple gases. They are complex carbon-rich compounds that normally require extensive chemistry and long stretches of time to assemble. Finding them this far away and this early is the problem. One explanation points to massive stars and supernovae cranking out dust and molecules at high speed. Another involves dense clouds where harsh radiation cannot penetrate, letting reactions run undisturbed for long enough to build complexity. A third says shocks from an active black hole are forging compounds through brute force. Webb read these molecules by splitting light into a chemical fingerprint. That fingerprint matched hydrocarbons that, on Earth, form through long, slow processes. Tiny dust grains acting as miniature factories where atoms stick, combine, and build into larger structures. But in this galaxy, those processes ran fast, or they started earlier than anyone assumed. Follow-up observations of other galaxies will tell us whether this chemistry is rare or common. If it is common, then the universe was seeding the chemistry that life needs long before most planets had even started forming. Number 7. Strange planetary phenomena. Webb pointed its instruments closer to home and found worlds breaking rules. One object drifts alone through interstellar space. No orbit, no host star. Yet it pulls in gas and dust like a miniature star, accreting at rates that make no sense for a lonely planet. It burns with heat it should not have. That one object blurs the line between planet and star so thoroughly that nobody is sure which word to use. Then there is K2-18b. Webb examined its atmosphere and found methane, carbon dioxide, and a faint trace of something called dimethyl sulfide. On Earth, that molecule comes mostly from oceans teeming with microorganisms. Scientists immediately said the obvious. These chemicals can form without biology, but the combination is unusual. The mix hints at a complex atmosphere with the possibility of liquid water underneath the clouds. Nobody is claiming life. What they are claiming is that the conditions are not impossible. And that is a sentence astronomers almost never get to say. For the rogue planet, the mystery is supply. Where does so much material come from to feed a world with no star? Some teams think it passed through a dense molecular cloud. Others suspect it was born more like a failed star that never quite ignited. For K2-18b, more spectra will settle it. The dimethyl sulfide signal either holds up under repeated observation or it does not. If it holds, the conversation about life beyond Earth changes permanently. Number 6. Unexpected galactic structures. Look at one of Webb's deep images of a galaxy from 10 billion years ago. You expect a mess, a blob, maybe a few clumps of stars scattered around. Instead, you see a spiral, clean arms, dust filaments threaded through them, old star clusters packed into the center, giant cavities blown open by stellar winds. It looks organized. It looks like it works. That organization is exactly what models say should not be there. At cosmic noon, when the universe was only 2 to 3 billion years old, galaxies were supposed to be rough drafts, lumpy, small, half-built. Webb found mature structures, barred spirals, thin stellar lanes, distinct thick and thin disk components, all of it billions of years ahead of schedule. How do you build the suburbs before the city exists? Some astronomers argue rapid gas cooling let disks settle faster than we assumed. Others say mergers, which usually destroy structure, somehow built it in the early universe. That collisions back then were constructive instead of destructive. The simulations are being rewritten. Stronger magnetic fields, more turbulent feedback, heavier dark matter halos that pull gas together faster. None of the updated models reproduce everything Webb sees. They get the spirals but miss the bars. Or they get the bars but miss the dust lanes. The universe organized itself far earlier than predicted. The mechanism that let it do that is still an open puzzle. Number 5. Cosmic voids. So the universe built galaxies faster than expected, but what about the places where it built almost nothing? Most of space is empty. The voids, enormous regions between galaxy clusters, contain almost no visible matter. Webb stared into several of them and found two problems. Some voids are too empty. They contain less mass than even the most conservative models predict. Others hold a few lonely galaxies that behave strangely, too faint, or forming stars at rates that do not match their size or surroundings. Webb mapped faint gas emissions and measured gravitational lensing in void regions. The mass estimates do not line up with what visible matter alone would explain. Something is off with the invisible part, the dark matter. Two ways to read this. Either dark matter is warmer or interacts with itself more than the standard cold model assumes, which changes its distribution in low-density regions. Or early stars and black holes blasted so much radiation outward that they suppressed galaxy formation in voids before it ever got started. Both explanations reach far beyond voids. If dark matter behaves differently in empty space, that shifts predictions for every galaxy, every cluster, every large-scale structure in the universe. The quiet parts of the cosmos are where the loudest questions live. Number 4. Unexplained brightness. There is an object called GNZ11. It is one of the most distant objects ever confirmed, and Webb keeps finding more like it. These sources pour out more light than our models allow for objects at their age and distance. No clean explanation. Webb spectra point to three possible engines: old stars that formed and aged impossibly fast, black holes that grew enormous in record time, or starbursts so intense that gas converted into stars with near-perfect efficiency. Each explanation fixes one number and breaks another. A physical constraint makes this harder. These objects are compact. All that light comes from a tiny region. Dense light trapped in a small space does not escape cleanly. Dust blocks some wavelengths, scatters others, and the resulting signal is messy to untangle. Astronomers are testing multiple angles at once, deeper spectra to read the chemistry with more precision, lensing checks to make sure nothing is being artificially magnified, time series observations to see if the brightness flickers, which would point to a black hole. Some models test heavier initial stellar masses. Heavier stars burn hotter and faster, flooding their surroundings with light before dying young. Each test eliminates a possibility. None has eliminated enough. The gap between what Webb measures and what physics predicts is real, confirmed, and growing with every new observation. Number 3. Dark stars. Here is one that sounds like it belongs in a different genre entirely. Webb may have found stars powered by dark matter. Not fusion, not gravitational collapse. Dark matter annihilation. Particles of dark matter colliding inside the core of a massive hydrogen and helium cloud, releasing enough energy to inflate the object to absurd proportions. 1,000,000 times the mass of the Sun, bright enough to outshine an entire galaxy. One single star. The candidates come from a Webb Deep Field survey called JADES. Several compact, ultra-bright objects in the very early universe do not fit the profile of young galaxies. Too bright for their size. Too compact for their luminosity. Spectra that carry features standard models cannot reproduce cleanly. Could they just be unusually efficient galaxies? Maybe. Gravitational lensing amplifying something ordinary? Possible. But the numbers resist a tidy answer, and the dark star model, proposed years before Webb even launched, matches the data uncomfortably well. If even one of these objects turns out to be genuine, the implications stack up fast. Dark matter interacts with itself. Dark matter can power a stellar engine, and when that engine burns out and collapses, it seeds a supermassive black hole, already large enough to skip billions of years of slow growth. Two of the biggest mysteries in physics. What dark matter does, and how early black holes got so massive. Potentially answered by one strange object. The smoking gun would be a specific signature in ionized helium emissions. Webb has the sensitivity, but the signal is faint. Teams are stacking data from repeated observations, trying to pull the pattern out of the noise. Nobody has proven it yet, but nobody has killed it either. Number 2. Unexpected behavior in familiar cosmic objects. Cassiopeia A is one of the most studied objects in astronomy. Supernova remnant. Mapped by every major telescope for decades. We thought we had it figured out. Webb found cold dust sitting inside blast zones where models say nothing should survive. Supernova shocks destroy dust. That is a basic prediction, well tested, widely accepted. Except the dust is there, intact. That matters more than it sounds. If dust survives explosions, then heavy elements stick around longer and travel farther through galaxies. That shifts when and where rocky planets can form. It changes what raw materials are available for chemistry, for geology, for everything that happens downstream. Beyond Cassiopeia A, Webb found filaments and knots in other remnants arranged in patterns that suggest magnetic forces far stronger than current models include. Around black holes, Webb mapped accretion flows at enough resolution to reveal shocks and cavities where clean inflow was expected. Nebulae that looked like smooth smudges through older telescopes suddenly show fine layers and sharp chemical boundaries. Explosions do more than scatter debris. They weave magnetic structures, grind dust into new forms, and send shockwaves that trigger the next generation of stars. Simulations updated with stronger magnetic fields and messier turbulence can reproduce some of these features. Not all of them. The gap tells us the physics of stellar death is more complicated than the physics we put into our computers. Number 1. Elongated galaxies. Every simulation of early galaxy formation makes the same prediction. Gas collapses under gravity. Collisions randomize the shapes. You get lumpy, roughly spherical blobs. Volleyballs, not surfboards. Webb found surfboards. A deep sky survey, called SEERS, revealed that the majority of galaxies in the early universe, between 50 and 80% of them, are flattened, elongated, stretched into two dimensions like threads and planks. Astronomers started calling them cosmic surfboards and pool noodles, which tells you how unexpected the shapes were. Round galaxies make sense under gravity alone. Elongated galaxies need a mold, something external pressing them into shape. The leading candidate for that mold is the cosmic web, the vast network of dark matter filaments that threads through the universe like scaffolding. If that is right, then the earliest galaxies did not just form near dark matter filaments. They formed inside them. The filaments shaped the galaxies the way a riverbed shapes water. Dark matter left its fingerprint on everything it touched. Invisible scaffolding, visible result. Some physicists argue warm dark matter or wave dark matter models produce smoother filaments better suited to explain these shapes. Others say cold dark matter still works if we rethink how gas settles inside halos. That debate ties directly into the biggest open question in physics: what dark matter actually is. Over billions of years, those stretched shapes eventually rounded out into the familiar spirals and ellipticals we see today. The universe grew out of its awkward phase. But now, we know it had one.